physical planar laminae, current rippled horizons in here, and the occasional sandstone kink within here. Now, this particular structure right here is actually a tectonic structure, not a depositional structure, but it does occur, and it's actually fairly common within our succession. I don't know if Murray's talked to you at all about Balma sequences. There is a very, very intelligent sedimentary geologist named Arnold Balma. Arnold was smart because Arnold chose to actually work on rocks that occurred on the coast of France. So he drank wine and chased after rocks back in the 1960s and 70s. But he became the world expert on these offshore deep marine deposits called Balma sequences. And all they are waning flow deposits. And this is right here is a Balma succession with the fine grain background sedimentation, the Balma A over here to the left, the Balma B right here, planar laminae deposited during high water currents, we refer to as upper flow regime, the water slowing down, producing ripples, and what we refer to as lower flow regime in the Balma C, and then background sedimentation, the D and the E towards the right-hand side here again. So pretty characteristic beds. What's cool about these rocks, of course, is that they are dominantly very fine sand and silt. And so we're looking at a muddy siltstone right here, a bituminous siltstone at the top right here, and a coarser siltstone bed right in here. This is a thin section right here, and I don't know if you have talked about thin sections in class, but thin sections are pieces of rock that we polish down to a very, very thin 0.08 millimeters in overall, 0.008 millimeters in overall thickness in this case right here. So they're incredibly thin chunks of rock. We shine light through it to see what the minerals are. And so in this case right here, I use different stains to tell my different minerals. And so what we're looking at right here are lots of quartz grains, lots of organic material we're seeing within these darker horizons right in here, almost no clay at all. And then porosity shown in blue, because we actually used a glue to glue this rock to a piece of glass, and that glue actually contained a blue epoxy, a blue colored dye, and so we can actually see the porosity within the rock shown here in blue. What's the red, you ask me? Well, I use different types of stains to actually tell different minerals, and so in this case right here, the bright red is actually calcite, and so we're actually dominantly looking at a dolomite matrix, so a magnesium calcium carbonate matrix, and calcium carbonate grains, just showing the overall mineralogy of the actual unit. Now we've talked about the lower part of the Montney Formation, the lower part of our lower Triassic. The middle part of our lower Triassic, shows a recovery of the biota. We start to see less acid oceans and more preservation of clams and snails and things along those lines. And so this waterfall right here is a bioclastic unit. It's a rock made of nothing but shell material. In this case right here, it's actually a bivalve or a clam called Chloria. That's just its genus name. And lots and lots of snail fossils, as well as brachiopod fossils in here as well. So that's actually this waterfall right here. The change in bedding is because of a change in lithology, change in the preservation, a change in biotic recovery after this extinction. Kind of cool that an extinction recovery can actually cause a waterfall. And there's a different shot right here again. You can see here again the gamma radiation, really clean where we go over that waterfall succession right here. Don't worry about that sequence band right there. All that is a time zone right here. We go from one geological stage into another geological stage in this unit right here. That word coquina itself is actually a Spanish word for little clam. And so it's a rock made of lots and lots of clam fossils. Kind of cool when you look at it in outcrop right here. There's actually see beautiful cross stratification in this bioclastic unit. All this right here is shell material within a sand matrix. Here's a chunk of that rock that's actually been broken out and polished up. And again, you can see all those curves right here. Those are all from shells. All of those are actually dissolved out shell material, and part of the rock is actually preserved shell material. So this entire part of the outcrop is nothing but shell. Real change in the nature of the rocks that we saw. I'll throw this in here too real quick. Does it matter to us? This is actually one of Western Canada's first oil reservoirs occurred within this exact unit. All that shell material right there produced amazing porosity and awesome permeability. Now, those are two words you might not really know that well. Porosity is simply the amount of holes in a rock. Permeability is how well are those holes connected. You can have all the holes you want in the rock, you don't connect them, your fluid won't flow. And so this is actually one of Western Canada's first major oil reservoirs right here. Jumping again, we're not that far from the town of Catamount right here. You can see this ridge right here, all these rocks dipping in this direction right in here. This river's right here because we're actually between two major thrust sheets. The front thrust sheet and a further in thrust sheet. I don't recall which one it is. Maybe Steve knows that. I don't recall which sheets we're on right here, but this river right here is the Whitehorse River, flows along, and we see all the rocks dipping in this direction right in here. So we actually have Paleozoic rocks in here, Triassic rocks sitting on top, and the next sheet over contains Paleozoic rocks again, with both Triassic and Cretaceous rocks on top of them. And that's actually where they're mining the coal. And so there's a road that goes past us. between that ridge and where I'm standing right in here. What we're looking at right here are the Triassic rocks dipping towards the west in this area right here. Really cool succession. And so what we're looking at again then, this is that coquinal, that brachiopod and bivalve and gastropod rock right here with that fine-grained siltstone here and the fine-grained siltstone sitting above that right there, producing this beautiful ridge within the White Horse Creek, right near where Drummond Creek flows into White Horse Creek. So I've talked lower Triassic this whole time. I want to jump a little bit into the upper Triassic now, or middle Triassic and upper Triassic. In the subsurface, all of our lower Triassic is called mountain formation. We talked about that. It's called sulfur mountain formation in a lot of the outcrop succession towards the west of Edmonton and the west of Calgary. We've also got these middle Triassic units. And so the Dobe Formation and the Halfway Formation, which are referred to as the Liard Formation in the northern part of our outcrop belt, these successions right in here are actually middle Triassic in age. And there's actually a major unconformity that goes across the basin that cuts through our upper Triassic, our middle Triassic, and right at the top of our lower Triassic. It's an angular unconformity right here that's actually a result of major tectonic disturbance in our outcrop and our basin. So it's a major tectonic disturbance in our basin, part of the mountain building that occurred early on, one of the first tectonic pulses in the Western Canada Basin evolution right here. And so we have this major unconformity here that cuts through from the upper Triassic through the entire middle Triassic into the lower Triassic. It cuts out somewhere in the ballpark of 25 to 30 million years worth of strata. It's an angular unconformity. In outcrop, these units right here are referred to in northern British Columbia. I'm going to show you some outcrop sites from northern British Columbia now, called the Liard Formation. The Liard Formation goes from the lower part of the middle Triassic into the upper Triassic. It's the upper part of that bed, this formation is actually upper Triassic in age. We start to see more coarse-grained rocks in here. I'll show you some examples of those rocks in just a second right here. And so what I'm showing you right here are a series of outcrop measured sections. This contact is actually observable in the outcrop right there. So we actually have a whole series of tidal inlet channels incising into a shore face succession. Nice sandstone successions. And these sandstone rocks contain an amazing diversity of fossils. Brachiopods and bivalves, gastropods, starfish of both types, both the blunt arm starfish and the thin arm starfish, so what we call asteroids and ophiuroids. There are echinoids in here. We are after the extinction. We're actually in the recovery interval in these beds in here. Here's the outcrop succession then. So remember, we actually have these measured sections here, the gamma on the side right there, showing the sandstone with the sharp contact right in here, bioclastic grainstone. In this case right here, water going in and out of the tidal channel is actually incising into the shoreline succession. So we can see this erosional unconformity that cuts into the adjacent shore face sandstones right in here. Really, really coarse grained strata with rip-up clasts of the adjacent shore face sand cutting into these clay and sandstone beds right here. All right, I'll show you a few more examples of different outcrop successions. One of the cool things about the Triassic successions is it's what we refer to as a mixed clastic carbonate system. And so it contains sand made of quartz as well as sand made of shell. And that's actually fairly unusual. And so in these successions right here, what we see is the waves pulling the coarse grain material towards the swash zone and keeping the clastic material, the finer grain quartz sand, in the lower part of our shore face. Really quite cool. We're actually seeing physical segregation, physical separation of these grain types within the succession. We also see lots of evidence in these areas of major deltas. And so unlike the lower Triassic, we've actually got major river systems now feeding into our coast. Things have become less arid, less desert-like, and more temperate, more Alberta today-like. And so how do we know they're deltas? Well, we see major evidences of sudden shifts in sedimentation. So the beds below me are actually concordant, deposited normally. The beds above this are deposited normally. But here we actually see major overturned beds within that succession. Another example of the same thing, you can actually see this whole succession of beds slid and rotated. And so the major bedding in this area is like this. It's the same below and above, but in this case right here, it actually rotated as it slid. Kind of cool. Other evidences, we see sudden changes, sudden deposition right here. And so right here, this is the outcrop gamma put over top of the outcrop right here. We see siltstone, lots of bioturbation in here, into a really sharp-based deltaic delta front shore face sand succession in here, back into the offshore right in here. It's a sudden change. If you actually look at the base of this outcrop right in here, the base of this right here, you actually see what we refer to as sand dikes, penetration features, where we dump a coarse-grained material into a soupy substrate, an unconsolidated fine-grained substrate, and it actually penetrates down in. So you see this thing right there. Oops, didn't mean to move that there on us. But you see, actually, I'll cut this right here. You can see that beautiful feature with sandstone penetrating into the silty shale right there. You can see that feature right there. And this is actually the bottom of this sandstone right there. Really cool. I want to talk real quick about some of the Upper Triassic rocks as well. We have some of the best Upper Triassic rock successions in the world. Now, you're going to ask me, what does it take to be the best in the world? Well, they're my rocks, first of all, so I like them that way. Those rocks actually contain an amazing record of life. We get into really awesome recovery in here and really diverse successions. One of the coolest things we preserve are actually ichthyosaurs, marine reptiles. We have an amazing outcrop succession preserving marine reptiles out there. And the ichthyosaurs we have are awesome. They contain tiny little things, probably the size of a otter. Ichthyosaurs, marine reptiles, are probably the size of a modern otter. We've also got ichthyosaurs in these successions in the Pardonay Formation that are somewhere in the ballpark of the size of a transport truck, of the size of a, maybe not a blue whale, but a sperm whale, a large whale, very, very large whale. I'll show you some shots of that in a few seconds there. And that includes our Triassic rocks. I'm going to ignore these next two slides. They're out of place right there as I do that. But this is the succession I'm talking about right here. And so we've gone from our Liard Formation down at the bottom part of our succession here into the Charlie Lake Formation, back into marine. So the Charlie Lake right here, the Liard is shore face. The Charlie Lake right here is non-marine, marginal marine. It's alien sand dunes, wind-blown sand dunes, and evaporates and what have you, back into a carbonate shore face right here, which is really quite cool. This contact between these light rocks and these dark rocks go into the Pardonay Formation. Now, if you look on that outcrop shot, you see that dark bed right behind the P in the Pardonay right there. That succession right there is incredibly condensed time. That little bed right there has more time preserved in it than the entire rest of the photograph right there. Really quite cool. We use different animals to date the rocks. And there's a type of animal called a conodont that we use to date the rocks. And the conodonts are incredibly common out here. Our conodont zones are each about 0.8, 0.9 million years or so. We have a bed that is actually somewhere in the ballpark of 6 centimeters thick that actually contains 4 different conodont zones, which is pretty amazing. It's incredibly condensed deposition. So we're going from our Charlie Lake Formation, which we talked about right here. This stipple pattern right here is our wind-blown dunes. We have the marine flooding surface on this contact right here, and getting into deeper and deeper and deeper water into our Pardonay. This succession right here is amazingly well preserved. I'm not going to blow over a couple of our slides right here. So I want to get into a couple of our better outcrop successions. I threw this in here. This is a vertical succession through our Upper Triassic rocks. Now it's pretty complex, so I don't want to walk you through everything right in here. But what's really, really cool out here is we've actually got this succession, which represents somewhere in the ballpark of about 8 million years from this green line right here where my cursor is, down into this green stipple pattern right here. And this succession right here, in this outcrop site at Pardonay Hill, that is probably at least as much time as this succession right here. Time is incredibly condensed. And so almost 100% of our rocks in this interval, in the Pardonay Formation, are either shell material, dead animals, or organics, dead animals or dead algae ultimately. That's pretty cool. And that occurs across the basin. Here's our Beldonal Formation right here. The Beldonal is shallow marine carbonates, like you'd see offshore of the island of Bali nowadays, or offshore of a Caribbean island nowadays. We have nothing but shell material in this right here. And then this right here is organics and shell material. Lots and lots and lots of algae, lots and lots and lots of shell material. Absolutely amazing. What types of shells? 1 trillion bivalves, 1 trillion types of clams, flat clams. They're really, really quite cool. Absolutely amazing stuff. This outcrop succession right here shows our Carnian-Norian boundary. This is actually kind of important for you. And I threw this in here because this is going to put this part of the world on the geological map. This is actually one of our candidates for that boundary. Now, Murray's talked to you and other people have talked to you about geologic time throughout the course. We as geologists can't actually deal with rocks without actually having some way to refer to time. But we don't preserve chronometers in the rocks. We don't preserve a little die, a little chunk of coin somewhere that says 4.4 billion years old, 3.2 billion years old, 1 billion years, 250 million years, etc. We don't see that preserved in the rock record. And so we actually have to come up with what's called GSSPs, Global Stratotype Sections and Points. Every time stage we talk about, the Cretaceous, or the Triassic, or the Jurassic, or etc., anything you deal with has to have an absolute physical spot that is actually reflective of what that time actually is. Every time unit has a boundary. or it's supposed to, and we're working on that right now. Carnian and Norian are two stages within the Triassic, and the Carnian is one of the upper Triassic stages, and Norian is the second of the three upper Triassic stages. We are looking at this outcrop locality right here to be the global stratotype section and point for that time boundary. We're still working on that right here. I threw that in there because it's kind of cool. It's kind of fun to work on to try and define what time actually is. This unit right here is called the Ludington Formation. This really heterolithic looking unit right here is called the Pardonate Formation. And it's really cool because the rocks themselves are nothing but fossils. Nothing but fossils. Every single lamina is a fossil right here. So you can see this coarser bed right here, these finer beds, all of them are jam-packed fossils there. If you look at a bedding plane instead of a vertical view, this is what you see. Shells upon shells upon shells upon shells for sometimes tens, hundreds, thousands of vertical meters. Pretty amazing stuff. Now, almost always, it's one or two types of bivalves, very commonly just one type of bivalve, and then the occasional ammonoid, which is those coiled-up thingamajiggies we saw before, and then bone material. And so you see these are vertebrae right here. These things right here, that's a forelimb of a marine reptile. These are ribs of a marine reptile in here scattered over. And so we're looking at a bedding plane with 1 trillion shells on it and one dead animal, one dead ichthyosaur right here, one dead marine reptile. But this right here is a tiny one right here. These individual vertebral centra, the central part of the vertebrae, are only in the ballpark of 8-10 centimeters across. The big ones are usually in the ballpark of dinner plate size, 30-40 centimeters across. Absolutely monstrous things. And the ichthyosaurs we had here are the biggest ones that occur in the rock record. They're monsters. And this is what these things would look like, kind of like reptilian dolphins, but they're huge. And so we actually had the monsters out here. This beast right here is something called Shoshonosaurus sickiniensis. Say that 10 times real fast. And Shoshonosaurus sickiniensis was around the length of a transport truck, a good-sized transport truck. And in fact, that skull itself right here, we only preserved 3 meters of it. In other words, that thing was at least a half meter longer than we actually have preserved. And so it's probably some of the ballpark of a 3.5 to maybe even 4 meter long skull. The woman right here is Betsy Nichols, the woman who'd actually discovered this along this river right here, the Sicanee Chief River. Really, really cool succession. But all good things have to come to an end. And so the Triassic ends, of course, with the beginning of the Jurassic. And we've actually got a pretty interesting Triassic-Jurassic boundary interval preserved in the Rockies. There's a place called Crying Grove Prairie. It's right in the Rocky Mountains, northwest of Fort St. John, south of Fort Nelson in British Columbia. Middle of nowhere, absolute middle of nowhere. And what we're looking at right here is 1 million Triassic clams over here, and then scattered Jurassic clams in this succession right in here. And you can see this boundary interval right here with these ripped up clasts and this phosphatic material. And it's another one of these major phosphatic rich horizons, radioactive horizons, right behind these guys' knees. And this is Chris McRoberts, Triassic clam expert, and Mike Orchard, Triassic conodont expert. Really, really awesome successions. Down south, the interval becomes a little more interesting. Here it is right here. These beds right in here are chock full of that same clam I talked about before, that Monotus subcircularis, 1 trillion of these bivalves in the beds. And we get into this boundary interval right in here. The first of the Jurassic ammonoids occurring here, the last of the Triassic conodonts occurring in this bed right in here. So it's actually a nice boundary interval, really, really cool boundary interval. There's been a few papers come out of that in the last little while. This is what that looks like from the air. I took this photograph when I was riding in the airplane of the outfitter, the hunting outfitter that owns the lodge that I use when I'm working up here. The door that I'm leaning out of right here, I shouldn't tell this to my department chair, but was actually held on to the airplane with baling wire. The door was actually going to fall off otherwise. And so he's flying along and I'm leaning out this photo thinking, God, I hope that wire actually holds tight. What we're looking at right here, these beds we're looking at right here are older towards the right-hand side of the photograph, younger towards the left. And we're looking at the Triassic-Jurassic boundary interval along this lacustrine succession. This is actually the dammed up Peace River, a lake called Williston Lake. These beds from this line right here to this line right here are 100% of those shells I pointed out before. Every one of those bedding planes, I'll just jump back up here. Every one of those bedding planes looks like this, 1 trillion of these large pecten-like bivalves, pecten-like clams. That's what all these beds look like in here. They disappear instantaneously right there. The last one appears right at that white line, and then all these rocks right here contain not a single one of those. They're completely and totally devoid of that. And that's actually the kind of a really cool change in beds, in fossils. Same thing right here. You can see all these white lines and these down in here. All of those are Monotus. And above that, it becomes black and massive, the occasional shell in here. And all of those are actually some type of different Jurassic or actually Rhaetian type of bivalve. I used to use a word you didn't understand, Rhaetian. That's the last time zone of the Triassic. All of this right in here is that interval called the Norian. From here to here is that interval we refer to as the Rhaetian, and then bang at that contact right there. That's the Triassic-Jurassic boundary in there. Again, big change. We don't understand that interval in the Western Canada Basin. We do not understand it at all. We've been doing a bunch of work on it, but there's a lot of weird things going on. And one of the sites I've never been able to visit, based on other people's outcrop work, actually contains a really, really cool looking unit that consists of nothing but bivalves, or not bivalves, of crinoid ossicles. Crinoids are an animal called a sea lily. They still occur nowadays, but they're incredibly common in the Paleozoic. And out there in the outcrop succession, we have an amazing succession of around 80 to 85 meters of nothing but crinoid ossicles in these beds. And I've never visited that outcrop locality. Big succession right in there. We know it actually occurs in that upper part right there. It's weird because it actually looks more like a European rock than a Canadian rock, but it's really, really quite unusual. So it's actually really, really interesting rock, something we're trying to actually get our handle on. I'm trying to figure out the Triassic-Jurassic boundary in the Western Canada Basin, where we know that it occurs in a very thin interval right in here, and actually includes a very, very major thick interval further towards the south. Really, really cool looking rocks. Now, I think the most important thing you can take away from a discussion on Triassic rocks is that extinction event and the recovery after that extinction. Life got wiped out at that point. We almost lost everything, but it actually opened up the doors to allow a lot of other things to come in. But at the end of the Triassic, which we're showing in this slide right here, we have another major extinction event. And we've gone through lots of those extinction events throughout the rock record. What caused that extinction, the second extinction? Again, we've actually got no real evidence it's actually a volcanic related event. Maybe it is, maybe it's not. Could be a bolide impact, a major meteorite impact. Maybe it is, maybe it's not. We're trying to get our head wrapped around that. We know that the world's oceans geochemically actually became very strange in this interval. And so we're doing some work trying to figure out why that is and what actually caused that. Maybe it is actually still related to the Triassic volcanism, but that's not actually a one-to-one correlation at this point. We don't know for sure. The Triassic starts off with a major extinction, it ends with a major extinction, and it's actually probably the most interesting time period in the rock record, and I'm not prejudiced there at all. What I would like you to watch on your own time here, and I've given you about an hour left, I kind of did that on purpose. What I'd like you to watch is this YouTube video. This is actually Benoit Beauchamp, a geologist from the University of Calgary, used to work with me at the Geological Survey of Canada about 15 years ago. Benoit's done a whole bunch of work in the Canadian Arctic. He actually discusses the Permian-Triassic boundary and its recovery after the extinction. That'd be worth you watching. So anyway, I'm going to stop my share there, and I'll take any questions you have on this. And if I don't know the answer, I'll lie to you. But I'm done with what I wanted to say to you guys today.
Okay, that's great. Thanks, JP. Now, hang on and just get everything. Yeah, well done. Well done. Now we could open the floor to questions. Maybe there won't be any at the end of today, but if we have some, we can get a hold of JP later.
Yeah, I'm available at all times.
Lots of silence. It was very nice, very jam-packed with information. Thanks, JP. Really good. Here, Ashley asks you a question.
Okay. There's huge areas with only one type of calamities. Actually, what's interesting about that, Ashley, is that we see that across the world. Is that related to the extinction? Certainly within the environment that animal is being deposited in, we don't see diversity. Yet what we're seeing there is a repeated pattern that occurs long after the first extinction and well before the second. It seems that during the first extinction, in deep water settings, we actually knocked off all diversity. And so these animals are actually probably living in anoxic settings, low oxygen or dysoxic, low oxygen settings, and using weird types of metabolic activities to obtain nutrition. And so we think these are actually hydrogen sulfide pumpers. They're actually creating their own bacteria to eat in a very, very unusual type of metabolic way. There's a whole series of these things. That animal that I showed you was actually something called Menotis. But before Menotis was Eomenotis, which literally translated means new Menotis. It's the older Menotis, the early Menotis. Before that, there was actually something called Holobia. Before that, there was something called Deanella. And so we actually had these flat clams, these pectin-like bivalves living in deep water settings, almost in one species types of environments throughout the Triassic. And it actually occurs right down to the Jurassic. We see the same thing occurring throughout the Jurassic. It seems that only a couple of things can tolerate these really, really tough environments to live in.
Now Nick is asking a question about the aquatic reptiles.
Oh, how did they get so big? You know, that's a great question. We don't know.
Well, they ate lots of little reptiles.
Well, that's the interesting thing. What I didn't talk about with that big reptile, that Betsy's big animal, Shoshonosaurus sickiniensis, the skull has no teeth at all. And it's not because they're missing. It's because it just didn't have any teeth. We think that that animal, like blue whales nowadays, were actually aquatic. We're actually plankton feeders. So plankton, plankton and zooplankton. So
good question.
Yeah, it's a really good question. It's actually really cool. It's actually, if you have a chance, go out to the Royal Trail Museum. That big animal, Betsy Nichols was an awesome scientist. She was tough as heck, and she was an amazing scientist. She died about, I think 16 years ago now, 2004, I believe it was, right after she described this, this animal. She went out there and collected it. It was tough collecting. It occurs right below a waterfall called the Sickening Chief Waterfall on the river there. It's a tough spot. It's actually cool because both Betsy and myself know where she knew where there were larger animals, larger fossils than the ones she collected, but they're all occurring at the tops of mountains. And you can't actually fly a 3.5-ton skull that's now rock, 3.5 meter long skull, sorry, that's probably weighing 8 or 10 tons. How do you fly that out of the Rockies? You helicopter can't carry it. You got to break it into small pieces. It'd be almost impossible to carry. And the truth is, I mean, what's the point in collecting another one? Same species. We've already got the biggest. We have the next biggest, next biggest. So, you know, this is the biggest marine reptile that ever lived, as far as we're aware. The Brits would actually argue with us about that. They have a 30 or 40 centimeter chunk of bone from I think it's Triassic in Britain, and they think it's bigger. But seriously, we've got an entire animal. You got a piece of bone. Shut up.
I agree. Isam's on your side.
All right, Isam.
Okay, Nick says thanks. Oh, Margaret has a question.
Oh, dinoflagellates. Yeah, so there's evidence of preserved dinoflagellates out there, but it's not proof. Dying because of the dinoflage. So that's actually an interpretation that people have used for major die-offs of lots of reptiles. In all honesty, I would argue that that's not the case with the reptiles we see up in the Triassic up north. The reason I say that is, yes, we may actually find closely spaced bedding plains with lots and lots and lots of reptiles, but if you actually look at it, you'll find a reptile in one time zone and the next reptile in the next time zone. We're not finding tons within short periods of time. The pardoned formation is a thin unit with an amazing amount of time wrapped up into it. It's interesting because the Norian interval is the longest interval in the Triassic, yet it's the thinnest stratigraphic interval in the Triassic. So did they die off by poisonings? It's possible. We can't prove that. Certainly in this interval, we don't see evidence of that. I know that from a similar standpoint, there's a major collection of marine mammals on the coast of Chile in the Atacama Desert, right on the right by the highway going down along the Atacama there. And that interval, there's good evidence that die off right there. The dozens of marine mammals are finding right there were killed off by algal poisoning ultimately, a large red tide type scenario. They've got evidence there. They've actually got some of the fossil material preserved in it. They got the fossil algae cysts preserved within their succession. They don't actually have. They've actually got real evidence. We don't see that in our interval. We don't see evidence of abundant dinoflagellates in intervals with the reptiles. Certainly, we don't see intervals with more fossil algae than we actually or fossil dinoflagellates than we find in other intervals that don't have the dinosaurs or the ichthyosaurs. So it's an interesting theory. It's got no evidence. It's worth actually noting for people who talk about fossil accumulations, there's two different ways you're going to get it. One would be condense a lot of time into one horizon, and you'll get a lot of material, or kill off a lot of material. You know, those are really your two choices for getting large accumulations. In this case right here, we've got a lot of time wrapped up into a very, very thin stratigraphic interval. It's not that we had 1 trillion ichthyosaurs, it's that we actually have ichthyosaurs preserved over tens of millions of years in a very, very thin stratigraphic interval.
Okay, it looks like everybody's quietening down, so I'll let you start signing off, and then I'll get these materials up on eClass by tomorrow morning, okay? Thank you.
Thanks all.
All right. Thanks, JP. And
I'll stick around as long as folks are here in case there's any more questions.
yeah, we'll watch them check out. Dawson says thanks.
Thanks, Dawson. Thanks all. So, Mur, are you and Stephen co-teaching this course?
Stephen's helped out every class. He, like we were stranded without one of our teaching assignments, so we've been doing it. But
okay.
I've been doing most of the lectures, and Stephen's been trying to correct me whenever I make a mistake. There's just not that many.
I've had nothing to do.
Right on. And usually Michelle Spila sits in because she's teaching the course in the fall.
I saw her earlier.
Yeah, she's doing just fine.
So this course is being taught again in the fall?
Sorry?
This course is being taught again in the fall?
Yeah, it is. It's going to go in September. I guess it'll go online again. So what we're learning now will benefit Michelle immeasurably.
Fair.
I'm just passing off all my notes again. She may well approach you to do the same thing for her course.
Fair.
But yeah, for sure. I'm passing everything to her in a shared Google Drive. This presentation will be in there, just so you know. But Michelle's pretty straight up. She wouldn't use anything without asking.
No, that's fine. Yeah.
Okay, that's good. Just gonna check some of these people.
Why everything's so fine grained in the Triassic? I mean, it's a long period of time of really fine grained silts and.
Well, it's fine grained silt in the lower and early middle, but in the middle we actually get into the half information, the yard information, actually have some coarser material, not a lot, but some. And of course, whenever we see coarse material, it's actually chert granules, up to chert pebbles. There's a few horizons that get coarser. Probably part of the reason is that I've always actually looked at this interval. The big difference between our Permian out here and our Triassic really is the extinction. There's nothing tectonically or structurally or environmentally different between the Permian Carboniferous and the Triassic. The big difference is the extinction. And so one of the reasons why we actually have so much silt is because we got rid of all the rest of the stuff. I think the Beloit Formation would be the exact same lithology if you actually got rid of all the shells that they have in the Beloit Formation. So we're basically looking at a carbonate platform without the carbonate.
Hmm. Yeah, it's quite striking.
So, even in the, I was actually doing some work and I got a request for a paper today that I'm like, that's weird. Why is he asking me for that paper? I'm not a co-author on it. And I looked at the paper and it turns out I'm not a co-author on it.